Welcome to a series of lectures called Glass, Selected Fundamentals, Basic Principles and Background Information. My name is Christian Roos. I'm professor at RWTH Aachen University and head of the chair for glass and glass ceramic. The purpose of this video series is to reinforce content of the basic lectures at my chair. The videos deal with selected aspects of glass science and are not based on the structure and thematic sequence of the lectures. This video is about the exploited heat in a glass furnace. The exploited heat, Hx, is, from a thermodynamical background, the theoretically needed energy to achieve a glass melt at a given temperature. The Hx is made up of two components. One is the chemical reaction enthalpy. That is the energy that is needed for converting the raw materials into a glass and the respective gases, and of sensible heat that is needed to bring all these components to the respective temperature. This relation can be written as seen here. So we have the exploited heat. This is the chemical heat demand for converting the raw materials to the glass, and this is a sensible heat. This term here, 1 minus Yc, depends on the Cullet fraction that is used in the process, because the cullet are already in the glassy state, so no chemical reaction enthalpy applies for the cullet. Now let's break this equation down. First we have the chemical heat demand, so the energy that is needed to transform the raw materials. The processes taking place in the glass transformation are mainly endothermic. Just rarely exothermic processes take place. So there is a heat demand for conversion of the raw materials. Because the starting and the ending of this conversion process is a function of state, it is of no importance if the conversion calculation is done at room temperature and then the respective latent heat is added, or vice versa. Now, for the calculation of the chemical reaction enthalpy, we come back to something that we have learned in other video, which is the vitrification enthalpy. In principle, the equation that applies for the calculation of the chemical reaction enthalpy is the sentence of Hess, which means the enthalpy of the products minus the enthalpy of the educts gives the reaction enthalpy. If the reaction enthalpy is negative, the process is exothermic. If the reaction enthalpy is positive, the process is endothermic. Let's first look at the enthalpy of formation of the raw materials. This part can be simply calculated by adding up the enthalpy of the respective component times their respective amount or mole fraction in the batch composition. The same applies for the gases. We have the enthalpy of formation for the respective gas component times the mole fraction or mass fraction of the respective component. Now, the same applies also for the formation enthalpy of the glass. However, here we have to observe that we take the formation enthalpy of the constitutional phase plus the respective vitrification enthalpy of that phase, and then again times the mole or mass fraction of the component. And by bringing these three parts together in this equation, we can easily calculate the chemical reaction enthalpy. So this is the first step for determining the exploited heat. Now, the sensible heat can be calculated by calculating the enthalpy content of the liquid phase, so of the melt, minus the formation enthalpy of the glass at the respective reference temperature, which usually is, in our case, room temperature, 25 degrees Celsius. The enthalpy of formation of the glass has already been determined in the previous slide, and the enthalpy content of the liquid phase, so of the melt, can be also easily determined by taking tabulated values of the enthalpy of the respective component in the melt times its mass or molar fraction. So again, we take here the concept of the constitutional phases. Now, the tabulated heat content of a phase in the melt refers to a certain temperature. In our case here, it is 1400 degrees Celsius or 1673 Kelvin. If now a sensible heat, so the temperature at which the glass is considered in the furnace, is different to this 1400 degrees Celsius, one has to adapt the equation according to the heat capacity of the respective component. This is calculated again with the heat capacity of the respective constitutional phase times the mass or molar fraction. And then we simply have a correction for the sensible heat in this equation, which takes the tabulated value for the heat content of the melt phase plus the respective delta in temperature of the melt to the reference temperature times the respective heat capacity of the liquidus phase. And now, by bringing these two equations from this slide and from the previous slide together, we can calculate the exploited heat in a furnace, which is the theoretical heat that is needed, as mentioned before, to transform the batch materials into a glass. Now, if we look at this Sankey diagram, where all the energy terms and loss terms of a glass furnace are shown, one can also easily see that the total energy that is brought into the furnace, H in, is related to Hx via the efficiency of the furnace, eta x. And the efficiency of the furnace is determined by all the loss terms that apply, which can be the structural losses in the regenerator, the flue gas losses, and all the structural losses in the furnace itself. So this relation here between the energy that is in reality needed to melt the glass and the exploited energy can also be written in this way. The in reality needed energy to melt a glass is the exploited heat plus the loss terms of the furnace. Or as written here, the total energy needed for transforming the raw materials into the glass is the exploited heat divided by the efficiency of the furnace. With this, we are at the end of this video, and I trust it was helpful for your further understanding of glass science.